So from our classification of uh, um, forward error correction code, actually we are covering block codes. We see another topic is a cyclic code. So we will actually discuss this cyclic code. Okay, this is actually in our syllabus. So our syllabus also covers BCH code and goalie code. Okay, let's see how far we can cover. So these topics today, now topics will be cyclic code. Okay. Okay, this is a cyclic code. So what is the properties of a cyclic code? If two codes was actually this is the same property for the typical block code, and is the first is the linearity. The first properties of the cyclic code is the linearity, which is actually we find in the linear block code. The second property is the cyclic shifting. It should be shifted. The code word, if you have a code word, they should be cyclically shift. We'll see in our example. After shifting left or right by any number of bits, resultant code should be again the code word. What does it mean? Okay, if I give you an example, things will be clear. Now the question is 4 code is given, 1, 2, 3, 4. Question is it a cyclic code? Okay, what is our first criteria for cyclic code? Linearity. Okay, what is linearity? Means actually you will add. So I'm adding this one with this one here. So 0 0 0 1 1 1 0 1 1 0 1 0 1 1. Is this code available here? Yes. So addition of these two code creates a new code, which is a linearity. Okay, again 0 1 1 0, which is actually this one, will be added to this one. So 0 1 1 1 1 0 1 1 0 0 1 1. So 1 0 0 1, which is actually this code. So this is the linearity. Again 1 0 0 1, which is actually this one. This one is added with this one. This one, sorry. So 1 1 0 0 1 1 0 1 1 1 1 0 0 1 1 0, which is actually this code. Means actually we find that okay, property of linearity is checked. Yes, it's actually linear. Now the second one, cyclic shift. Let's see if this is cyclic shift. Okay, you see 0 0 0 0, it will be 0, so cyclic shift will be same, there is no change. So we will not give this example. We took this one, 0 1 1 0. So 0 1 1 0 means actually they will be shifted. This 0 will be shifted here, which is 0. You see 0 0 1 1. Is it anywhere in our code? No. So this is not a cyclic code. Means this code is not a cyclic. The series is given is not a cyclic, because the shifting properties do not satisfy. There is another example, that whether this is a cyclic code or not. Okay, same thing, we check the linearity. The linearity checks out. Linearity is okay. Now the shifting, you see 0 0 0 0 and 1 1 1 1, either way you shift, they will be same. There is no point of consider these two, shifting it. So we will try with other two, this one and this one, which is actually here, this one and this one. Okay, so 1 shifted, 0 shifted, 1 shifted, 0 shifted, and 1 shifted here. So they create 1 0 1 0, which is actually our. So 0 1 becomes 1 0. So this code becomes this code. Means actually it follows the cyclic. Okay, 1 0 1 0, it creates 0 1 0 1. Means actually this code, they are actually interchangeable. These codes are interchangeable by shifting. Mean shifting properties checked. So we called it of yes, this is a cyclic code. Yes, so this is a cyclic code because the linearity property and the shifting property checks out. Okay. Okay, so the next we will talk on the cyclic code for non-systematic code word. So what is a cyclic code, we understand what is a non-systematic code word. In a non-systematic, what is happens in a systematic code word. In a systematic code word is always combination of the message and parity. They are in sequence. Means first part will be the message part, the last part will be the parity part. If this is the way, then we call it systematic. If it's not, then we call non-systematic code word. Okay. So how the non-systematic code word will be generated? Directly from the message and the generator matrix, or here generator polynomial. Okay, so C is the code word polynomial, M is the message polynomial, and G is the generator polynomial. Polynomial is easy, we'll see. So here let us give an example, how to generate polynomial. So okay, polynomial. There construct a non-symmetric cyclic code 7.4. This is 7.4 code using a generator polynomial. This is a polynomial is given with a message is given. Okay, so this is our message code. Message code is 1010. So 1010. We can convert it as a x to the power 0, x to the power 1, x to the power 2, x to the power 3 to create as a polynomial, isn't it? So you see actually how it will be translated. So it will be 1 into x to the power 3 plus 0 into x square plus 1 into x to the power 1 plus 0 into x to the power 0. So 0, 0, 0 is gone. So we have x cube and x1. So that's actually x cube and x to the power 1, which is actually message signal. Means actually this message signal, you see this 0 and this 0, they actually will in our polynomial they will make this part and this part 0. Okay, so we have x to the power 3 and x to the power 1. This is our message signal, and generator matrix is already given. x3 x to the power 3 plus x square plus 1 is given. So C is nothing but this multiplied by this. We already convert our general message to the polynomial form, and generator matrix is already is given in the polynomial form. Okay, so you will actually we multiplied out. Now we see here, you see x3 and x3 become similar. If you do XOR, then x3, you see 0 0 and 1 1 is always 0 in XOR. Means if they are similar, they create 0, because this and this is similar, so we can cancel it out. What remains? X6, x5, x4 and x1 or x to the power 1. Now here I can actually spread it out. x6 is nothing but 1 into x to the power 6. x5 is nothing but 1 into x to the power 5. 4, 1 into x to the power 4. x3 is missing, that's why we multiply by 0. So 0 into x to the power 3. So x2 is missing, so 0 into x to the power x square, and x1 is here, so 1, and plus 1 is missing here. There is nothing, so we multiply by 0. So what will be our code? Our code will be 1 1 1 0 0 1 0. So 1 1 1 0 0 1 0. That will be our code. You see how if you have a message signal and you have a generator matrix, easily you can create a code. Got it, guys? Got it, guys? So here what we say, this is a non-symmetric. Non-symmetric means what? This code word contains this message 1010. 1010 is somewhere in this message. So I don't know which one. 1010. In between probably they are the parity bit. But it will be more clear if we take an example of the symmetric code word. So in symmetric code word, the code word will be generated by this. Cx is nothing but x to the power n minus k message signal, parity signal or parity code. So where parity code is nothing but the remainder of this product. This divided by this bracket is missing. Okay, because this is symmetric code word, what will happen in symmetric code word? First part will be the message properly, and the last part will be the parity properly. Okay, probably it will be more understandable if I give you an example. So in example we are given a 7.4 code, and the generator matrix, and the message is given 10. This is actually the same one, 1010, same. Previously it was a non-symmetric, now it's a symmetric. Okay, so this is 7, 7 means n equal to 7. This is nk, message is 4, which is actually k also, it can be written as a k. So rest of the 3 bit will be actually, so 4 bit message and 3 bit will be the parity, it makes total 7. So message bit 1010, I can convert it to the polynomial format, x to the power 0, x to the power 1, x to the 2, x to the 3, because this is 0 and 0, they will not consider, so x to the 3 and like the previous one. Okay, so this will be our code word where we do not know the parity yet, like this formula. This is our total code word, and this parity we have to find it from this formula, parity. Okay, let's find the parity. Here parity is nothing but the remainder of this 2. So x, what is n? N is 7, k is 4, 7 minus 4 is 3, so this is x to the power 3, and mx nothing but this one, so x to the 3 plus 1, x to the 3 plus 1. Okay, what is gx? Gx is given the generator matrix, which is given here, x to the power 3 plus x square plus 1, which is actually this one. So now we know this one, this is actually this amount divided by this amount. What will be the remainder? That value will be the p value. So here we actually divide this one. So x to the power 6, you see, x to the power 6 plus x to the power 4, this is divided by x to the 3, x to the power 3 plus x square plus by this one. This will be divided by this one. General math, Okay, so we have to match x to the power 6, we take x to the power 3. So it will be x to the power 6, 2, x to the power 5, and this x to the power 3 into 1 will be x to the power 3. So 6 is gone because they are XORed. They will be XORed. Okay, what remains? X to the power 5. Oh, so what we will take? So we will take x to the power 2 to match it. Okay, so we have x to the power 2 into x to the power 3, 5, 2 to 4, 2, 1, x square, 2 and x, this x cube. Okay, so what do we have? X to the power 5, x to the power 4, and so 5 and 4 they are gone. X to the power 3 and x to the power 2 remains. So x to the power 3 and x to the power 2 remains. What happens? 1, then x to the power 3, x to the power 2. These two matches. So 1 remains. So this 1 remains. So this is the remainder. So that remainder is the result of the remainder. So px parity will be the remainder is 1. So put back in the formula. So this p will be 1 if we will find the code. Okay. So what we did, we actually write this code here. So we know x, n is 7 minus 4, 3. So this is the mx, and p will be 1. So we know x6, x4, x1. So we say we can be write it as 6 is there, 5 is not there, so it's 0. 4 is there, 1. 3 is not there, so it's 0. 2 is not there, it's 0. 1 is not there, it's 0. And this 1 is here, so it's 1. So you see 1, 0, 1, 0, 0, 0, 1. 1, 0, 1, 0, 0, 0, 1. So you see our message 1010. This is given previously 1010. So this is actually 1010. This is actually message, and this is the parity. You see our systematic. That's why first one was message, means actually this was parity. 01001 is the parity. So we created a code word. Got it, guys? Guys, you either got it or you don't got it.
Yes, sir, we got it.
Okay. Now, so it's easy. It's like very for fourth year is like very easy stuff. I'm not actually giving you theory because who cares about theory if you understand the example, eh? So you do not have to memorize it. Understand it, explain it in your own way. Do not memorize anything. Understand it. So we covered cyclic code. Okay, what means today we will actually give you a fundamental of BCH code. We will not actually in this class we will not study very detail of BCH code. It's like very like long topic. I will actually introduce you with the BCH code. Okay, in this section, BCH. What is BCH? BCH. So what is BCH? Okay, so the BCH code. BCH code is actually a subclass of cyclic code, the code we just studied. This is actually a subclass of the code. But how the BCH code? So who proposed it? It's from this name. From the name comes Bose, Choudhury, Hockingen codes. So actually three guys, these two guys independently, and this guy, French guy, they actually simultaneously proposed this code. That's why it's called BCH code. It's actually part of a cyclic code or subclass of cyclic code. So you see, so far we have seen that our block code can someone like event parity can only detect an error, cannot correct an error. Our linear product code, um, product parity code, it can actually detect one bit. If it's multi-bit, it cannot detect. BCH can do multiple error correction. It can detect multiple and it can correct multiple. So the block length will be n 2 to the power n minus 1 and the distance will be, so these are the condition here. Okay, so number of message bit k is by this condition. Okay, here we introduce a word. Each BCH code is a T error correcting code. Means multiple, you see multiple, so that multiple is T. How many? T means 2 or 3 or whatever. I mean it's greater than 1. So each BCH code is a T error correcting code. In that it can detect and correct up to T error per code. It can do multiple error correction and detection, multiple error detection and correction code. Okay, so here we will see a new generator polynomial which is called GX, like the previous one, which is actually comes from the messages, but they will be LCM. LCM is the least common multiplier. If I have a message 1, message 2, message 3, then from their least common multiplier, LCM is called short term is called LCM, is called the generator matrix. Actually, say what does it mean? Least common multiplier. You see, if I say what is the least common multiplier for 4 and 6? So we know for what is the multiplier of 4? 4, 8, 12, 16, 20, 24, 28. These are the multiplier of 4, right? Isn't it? What is the multiplier of 6? 6 is 6, 12, 18, 24, 30, isn't it? So who are the common between them? This 12, you see? 12, 24. So who are the least multiplier of 4 and 6? 12, 24, blah, 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 blah. That is called least multiplier. Okay. So we actually, you have to find the least multiplier from this M1, M2, M series. Okay. Up to which one? Up to twice of this error it can correct, T value. This is all about theory. Eh? Okay. So the degree R of this nk is nothing but this n minus k. So in the degree of BCH code, n So we can rewrite is that k equal to n minus r. Okay, so we find this four quantity. So this is the formula k n minus r. We know k has to be greater than n minus m, and n is 2 to the power m minus 1. These are the and the minimum distance. We will actually see probably in an example. Okay, so small example. Construct a triple error correcting code. From its name itself, means T is, you see, correcting code T. How many? T. So this T value is 3, triple. It can correct 3 code of VCH code with block length n equal to 31 and over GF equal to 2 to the power 5. What is the GF means? Goal-ice field. Goal-ice field actually is also called finite field. It's actually very much today's lecture we cannot cover it, actually it's too wide. We'll see in if I have a scope, I will try to give you a little bit idea of this Goal-ice field. It's actually used in the crypto in science or engineering or coding theory, where like crypto information crypto cryptography blah blah blah, there actually is very much used. Okay, just familiar with this term GF, Goal-ice field. Okay, this value is given. For the time being, we will not bother about this one. Okay, so from this word we can say T equal to 3 because it's triple error correcting code. So GX will be LCM of what? You see how many LCM? LCM will be up to, is T is 3. If T is 3, then it will be up to 6, right? M6. So that's why I write it M1, M2, M3, M4, M5 up to M6. Okay, so here this part I did not explain here because we did not study GF, Goal-ice field. So Goal-ice field for 2 to the power 5, this will be the message created for M1, M2, M3, M4, M5 and M6. This will be our separate scope of the separate study. If I will upload a separate lecture or I will explain it separately, not this class, because it's totally actually a separate lecture. Okay, just we are assuming, okay, these are the M value up to M6 based on this GF. Now here what we will say, you see this up to M6, they are actually a half. You see M2 is nothing but M1, M4 is nothing but M2, M6 is nothing but M3. Means actually this M1, M2 and M5 they are actually covers. M1 covers what? M1 covers M2, this M3 covers 3 covers M6 and M5 covers where is M5? M5 is here. Means actually they're already reduce the value. Once we reduce the value, the LCM is no more considered actually, because these are the common term. I give you an example. If you do the LCM, then the common terms, you see, if you write 12 and 14, it's no more the MCM. This is the normal value. You can write LCM of 46 is equivalent to this one. Same thing I did here. When I write LCM of this whole series is nothing but of this common series. So actually what I did, actually I put M1, M3, M6 from here. M1, this one, M3, this one, and M5, this one. Multiplication. All the multiplication will give you this value. Simple. I am not going in detail of this one. From here we say, okay, we know this formula k equal to n minus. So we know n. This is actually here. You see the block length n equal to 31. So we know, okay, this is our 31, and m2 we know m is 5 2 to the power 5. This is m 2 to the power 5, and t is 3. So we say k equal to 16. Same way we find this m equal to 5. So nk, so this is n equal to 31, k equal to 16, k equal to 16. This is actually a 3116 code, which is actually we are talking about here. This BCH code that we are talking about, this is actually nothing but a 3116 code, nk. This is just for like introduction of the BCH. We actually lots of things to be discussed. like this Golis field and all other stuff. So in other separate lecture, I'll give you detail of this BCH code. Okay. So that ends our lecture today.